Hello, and welcome to ASL demola. And today's lesson, we are going through rates of reaction. Very, very important topic, building on from our ideas from GCSE. Let's see how quick we can go. Let's get it.
Okay, so we're going to start things off with a definition, being that the rate of reaction is equal to the change in the concentration of a reactant divided by time. It can also be the concentration of a product as well. In terms of measuring rate, we do need to know how to do this experimentally, but essentially we'll either be doing mass loss, volume of gas produced, color change, pH change, or electrical conductivity. With regards to your A level, really, to be honest, the main two that you're going to focus on are these ones. So mass loss and the volume of gas produced, which is why I put stars next to them, and I'm highlighting them in green. So just know that those are the main ones that you're going to be working with in A level. Now, we need to define what a successful collision is. This is one where the particles collide in the correct orientation and with sufficient energy to overcome the activation energy that's written as EA throughout this whole video. So, not only do particles need to collide, they need to collide in the right orientation and with enough energy. So, what factors are at play here that are going to increase the chances of us getting a successful collision? Well, one of them is going to be the concentration and the pressure, right? Concentration and pressure essentially means that we're going to have more particles in a confined space, yeah? Concentration, normally when we're talking about liquids, pressure when we're talking about gas. But in terms of your exams, you need to use really important language that's going to help you to get the marks. And that language is going to be more particles per unit volume. So particles per unit volume. So with regards to concentration or pressure, what we're going to say is there's an increase of particles per unit of volume. Hence, there's an increased frequency of successful collisions, which means we increase the rate of reaction. That's the kind of process I want you to go through. Similar with temperature, if we have more temperature, these particles can start to bounce around more, they'll move around more because they have kinetic energy. So if we have increased kinetic energy, then that means that the frequency of successful collisions should also increase because the particles are going to collide more often. Well, yeah, they collide more often and with more force. And that's the kind of idea we're getting at there when we're talking about factors affecting your rate of reaction. Another thing I wanted to show you was graphically, you might be given a graph for us to like join the spots on a graph, and then with that, give you information on the rate of reaction. I just wanted to show you that because these graphs are normally curved, we can't just calculate a rate just like that. So you will probably have to draw a tangent to the curve at a specific time. Let's say they asked me for the rate of reaction at, I don't know, 10 seconds. Then you see, I go to 10 seconds, draw the tangent there, and then calculate the gradient. That will give me the rate. Something else your spec wants you to know is the importance of catalysts. So, a catalyst is a chemical that lowers the activation energy without being used up by offering an alternative reaction pathway. This is something that I believe you should have covered at GCSE. Now, in terms of catalysts, we have two types, homogeneous and heterogeneous. And basically similar to other things you would have come across in chemistry and biology. Homo, same, hetero, different. So homogeneous, means the catalyst is the same state as your reactants, whereas heterogeneous means that the catalyst is a different state to your reactants. And literally what you will have to do is they'll give you the catalyst, they'll give you a reaction, look at the state symbols and make your judgment based off that. I also wanted to bring back these enthalpy profile diagrams, which we've seen before. You should be able to tell me, is this on endothermic or exothermic? Newsflash, it's exothermic. So, in terms of the activation energy, when we add the catalyst, as you can see in the graph in red, we've lowered the activation energy, meaning this reaction can occur a bit more easily, which is obviously going to help us out. So definitely know how to manipulate these curves to do that. I'll just quickly draw on now, but if we had an endothermic reaction, where the reactants are here and the products are there, the products are here, just know that your new graph would kind of just look like that. So very similar ideas kind of going on. Okay, and here's the new big idea that we get at A level. You have your Maxwell-Boltzmann distribution curves. And these are really important in terms of telling you about the kinetic energy of particles at a given temperature. Yeah? So, axis is really, really important here. You can see on the y-axis, we have a number of particles. On the x-axis, we have the energy. So be able to say those. You can like substitute things in, but definitely look at your exam board for that. Now, there are key things we need to know over a Boltzmann curve. First of all, before we get into the nitty-gritty per se, that needs to be at the origin. Start the graph at the origin. And most are going to say, this does not touch the x-axis. Don't let that touch the x-axis. Cool. So those are like two things to know whenever you're drawing it, because you will be asked to draw these in exams. Make sure you know those things. Now, up here, a bit less examined, but you can see here, this is where we have the most amount of particles. So this must be the average energy of your particles, or code word, your median. Yeah? Cool. Another important thing to say is here, we've got activation energy here, and you can see all the particles that have above the activation energy, they can react. So they have enough energy where if they collide in the right orientation, a reaction can occur. Yeah, know that, and just know as well the area underneath the curve. This is kind of the last bit. All this area underneath the curve, that's going to be the total number of particles. So you can see here, the y-axis is giving us the total number of particles at a given energy, whereas we're saying that the area under the curve is going to be the total number of particles in whole. Now, temperature changes affect your Boltzmann curves. Like we said, it represents kinetic energy at a given temperature. If we increase the temperature, you need to know these changes. The graph's going to shift towards the right, as you can see. It's going to become less steep, and we'll see that there are more particles of the activation energy versus these red ones and the blue. Hope that makes sense. Similar idea for if the temperature goes low, essentially the opposite, where the graph's going to shift left and become steeper. Yeah, and this now means that less particles, you can see the ones in blue at the bottom, less particles are now going to have or exceed the activation energy. And the last thing with the Boltzmann distribution curve is what happens when we add a catalyst, right? So we said it offers an alternative reaction pathway, reduces the activation energy. So we literally just shift the activation energy to the left. Yeah. If we shift it to the left, we have a bigger platform with more support that's going to help you. So catalyst reduces the activation energy, meaning that more particles have or exceed the activation energy and can make successful collisions. Hence is why you get this. Okay, we keep on soldiering through to the questions now. So you got the first question, which is going to ask you to draw a Boltzmann curve and also explain why increasing temperature increases the rates. We have this one where a graph shows the reaction getting slower over time. Don't really worry too much about it. It was a concentration time graph. You don't need the graph to answer that question. And then finally, they've got this one. They will need to talk about initial rate and also about predicting the sign of the enthalpy change. Okay, so for the first part of the question, we were drawing the Boltzmann curve, right? And you can see here, T1 is probably your lower temperature, whereas T2 is a high one. So you can talk about, probably we'll say here, about shifting and everything like that. Yeah, so to the right, and you got a lower maximum, so it's less steep. So those are really important things when you're doing higher temperature. Now, I mentioned before, proof I'm not waffling, we really needed to talk about your labeling axes. You see here, kinetic energy and number of molecules, very, very important. Again, we said, must start near the origin. So within the first square next to the origin, and also must not touch the x-axis. So these are really important things that they will look for in your exams. Now, that's about that, yeah. So we've kind of talked about this as well. That was the key thing for this question. Sorry about that. Cool. Then for the next question, we were talking about concentration, right? So if we have a reaction going on, then we're going to be using up the reactants, right? So that means there's going to be less reactant. So if the less reactant, because it's being used up in the reaction, being formed to a product, the concentration is going to go down. And we said if the concentration goes down, there's fewer particles per unit volume. I know it doesn't say that specifically on this one, but they do. They really, really, really do emphasize it. So I'd always say less particles per unit volume. And then we can say less frequent collisions. Yeah. And we can see here, it stops when all the reaction is used up. I know I did not give you the graph, but that's kind of your general gist whenever you have something like that. And then I forgot to warp it out. Apologies. But yeah, what we're saying is that for this question, they asked you, let's just look here, explain the difference in the initial rate and predict the sign. So you can see here, at higher temperature, you'd expect particles have more kinetic energy. So they're going to collide more often, more frequent collisions. So we had a faster rate. More particles have or exceed the activation energy, which is why the rate is going faster, right? Don't worry about this part because I didn't give you enough to do this bullet point. Why is it exothermic? Well, if we go back to the graphs, you can see here that at 50 degrees we're forming more product, or the absorbance is higher. At 90 you're forming less. So that tells you when you increase the temperature, the equilibrium is probably shifted to the left, which would mean that your reactions are exothermic. Equilibrium we're going to cover in a video quite soon. Okay, and obviously we're going to wrap up with the A-star tips. So what's good? Terminology, really crucial for this topic. Saying things like particles per unit volume, like successful collisions, particles having or exceeding the activation energy. Those are things that examiners will look for in the math scheme, which will help you to get marks. Tangents, accurate, ruler, please. Don't freehand a tangent like this. They'll mark it wrong instantly. To be fair, I was saying that like, this powder line is actually quite good. But regardless, use a ruler. Don't freehand it. Yeah? Cool. Boltzmann curves, be really good at that, because that's like cash money in the exam. Yeah. So making sure that you're near or at the origin, making sure that you don't touch the x-axis, making sure that what else? Making sure that the curves are less steeper, they're shifted to the right or the left. Make those really clear in the exam, so the examiner will basically be in love with whatever curve you draw. Now, so my handwriting's gone a bit pear-shaped here. I was very tired. But in terms of what not to do, units, or labeling axis, really important. And we saw it in the mark scheme. Make sure you know those. Experimental methods for calculating rates. They can ask you like a 6-marker practical question about that. So make sure that you know, and you should have done those experiments in class, I believe. Yes, products versus reactants. So that's kind of what I tried to draw here. I'll just draw it again. When you have a graph that's talking about like the concentration of a reactant over time, it will normally be a downwards curve like this one in blue. Whereas if we're talking about the product formed over time, it'll probably be an upwards curve like that. So just make sure this is for product, that's for reactant. So make sure you know what you're dealing with. And then catalysts are beneficial for a lot of reasons. Can be saving money because less energy demand, can be less emission of carbon dioxide or fossil fuels. Just make sure that you're relating it to the question, obviously. But make sure that you do know a couple of reasons why. So that has been this video. If it's been useful, please like and subscribe to the channel. Any questions at all about anything I've said today, comment below. I'll do my best to answer. We've got our TikTok and our Instagram, both at A-star demola. But that's all for me for now, and I'll catch you in the next one. Bye for now.